So, please sit. The last lecturer of the school also comes from Israel, from Holon Institute of Technology. He's an electronic engineer. He's an assistant professor in Holon Institute of Technology. His specialization is like in lasers matter interaction. Again, we will be focused on the biology-related subjects and how lasers they can modify the properties of this kind of materials. The floor is for yours for 45 minutes. 10 minutes before the time, I will waive you. Okay? So just concentrate to finish happy. After we finish, we are going to have a photo in order to count how many of you have survived after 3 days. Okay?
Well, thank you, everybody. Thank you, Kostas, for...
Quiet, please, quiet now, please.
Okay, so thank you. It's a pleasure to be here in Milano. And it's a pleasure to be the last one when everyone are tired and very eager to learn. So my lecture is a mix of educational and research-oriented presentation. And the topic is linear and nonlinear optical properties of bioinspired peptide materials. So I will explain, we will start by explaining what are these materials, and then I will show you how I characterize them by optical means. Okay, so first, I guess you wait. Oh, okay. So you know this guy, I guess. So Steve Jobs said that. I think that the biggest innovation of the 21st century is the intersection of biology and technology. So we focused on this interaction. So we see how biology, compounds and materials, in terms of material science, can be exploited in many optical, we are interested in optical machines, optical photonic integrated circuits, and more. So the goal of this lecture for me is to show you how your accumulated knowledge so far in this school can be implemented in material science research with the aim of characterization of peptide structures, which I will explain to you now. So first I will discuss on some introduction about this kind of materials. Then I will show you their unique and mysterious property, which is mysterious, so I will talk about it later. Then some of their nonlinear optical properties, which are related to second harmonic generation. I think that there were few courses during these schools about this phenomena. Then I will show you a new paradigm that we developed, which is peptide integrated optics. This is how we call it, and then I will finish and summarize everything. So first, an introduction. The story begins with biology and self-assembled structures. So self-assembly is a process that molecules without any external direction or external energy are self-assembled from unorganized form to an organized form spontaneously due to all kinds of interaction, pi-pi interactions, hydrogen bonds, whatever you want. And usually it is in a solution. So there are many types of self-assembly. One of the most famous ones are the amyloid fibrils. Amyloid fibrils are fibers that are related to many diseases in the human brain. For example, in Alzheimer's. So much research is done to investigate this kind of plaques. So when they opened a person with a person's brain that had an Alzheimer, had in the past, yeah, because he already died and they opened his brain. So they found out that there are many aggregates of some mysterious protein, and now there is much effort to understand why these kind of fibers, which are nanometer size, okay, why they generate, why they are fabricated by the brain, or no one knows. I mean, and the thought was maybe we should eliminate them and then to cure the Alzheimer, the Parkinson, many more diseases. So much effort was done on this topic, and the characterization of this kind of amyloid fibrils was also done. Inspired by these amyloid fibrils, in 1993, the first, let's say, research was done on bioinspired peptide nanotubes, which are synthesized, okay, peptides, which are composed of amino acids. I will talk about it soon. And then Gadiri in 1993 showed that he can synthesize by self-assembly all kinds of nanotubes which have a circular cross-section, and started to investigate them. And he was actually the first one who started this kind of, opened the way for these kinds of materials. And all these nanocrystalline building blocks are, of course, linked by non-covalent bonds, which allows the properties that I will discuss later. So, okay, if we're talking about peptide nanostructures, so the process begins like that. We start with some monomers, which you can see. Where is the laser? Oops. Oh, okay. So we start with here. This is the primary structure of the peptide, so some kind of sequence of amino acids. Amino acids are the building blocks of peptides and proteins. In the human body, in all real life, there are 20 types of amino acids, okay? So they are molecules with amine group, carboxyl group, okay? And actually, they also encode our genes, and they are very important. For example, before I start, phenylalanine is something that is in every diet beverage that you drink, is because of the aspartame, okay? The sweetener aspartame. So many kinds of amino acids are either essential to the body or non-essential to the body, and phenylalanine, for example, is essential for the body. So if we take a sequence of peptide structures, for example, the phenylalanine, one of them, then they assemble into secondary structures. Normally, there are two types, the alpha helix and the beta sheet. It's a three-dimensional organization of these kind of molecules, okay? Then they are self-assembled into their, let's say, architectures. They can form almost any type of shape. They can be rectangular, they can have hexagonal shape. I will show you later all kinds of different variety of these structures. And they are composed of building blocks. You can see here, we can talk about peptide engineering. So these building blocks actually assembled the entire shape of the three-dimensional peptide structures. Okay, so this is kind of a new generation of bioinspired materials. So this is a subcategory in material science that deals with all kinds of materials. So for this is not biologically net biological compounds, but they are bioinspired. This means that we buy a powder of all kinds of peptides or amino acids or proteins. They are not naturally occurring in nature, and then we start to use the self-assembly process to get all kinds of shapes and crystallized formations. Okay, so I want to talk about to put a special focus on the diphenylalanine peptide microtube, which is here. So we talk about amino acids. If we take a long chain of amino acids, we create something that is called a peptide. Very long chain is a protein, okay? So the amyloid fibrils that I talked about them 2 minutes ago, and in the missing puzzle here in the brain of someone with Alzheimer, and here is a photo, as you can see, of the nanometer size of the fibrils itself, are composed of this kind of long chain of amino acids. Every letter is a different amino acid. So if we are talking about the phenylalanine, which symbolized with the letter F, is here, this is aromatic amino acid, which means that one in the past, we thought that this kind of aromatic side chain, okay, stabilized the entire amyloid fibril. So the thought was maybe to eliminate it, destroy this kind of amyloid fibrils, we should somehow kill this bond, okay? So to disconnect the aromatic side chain. So, but the interesting thing is that when you take the large chain, which is composed of all the amino acids, we see that in the middle there is 2 phenylalanine. We call it diphenylalanine. So in the lab in 2003, the researchers synthesized only these diphenylalanine compounds. Then they made a very simple process. They put it inside some acids, and then they added water, and suddenly they get something like that. So this is an hexagonal microtube, okay? Which you see the hexagonal cross-section, you see here. They are hollow, okay? And then they got, as much as Gadiri in 1993, they got a new peptide microtube or hexagonal microtube. So you think to yourself, what do I care? Why it is interesting? Okay, so I will show you later why. You still can argue with me if it's interesting or not, but I will show you, hope to convince you that it may be interesting. But before, I want to also talk about the secondary structure. So usually the second structure is measured by something that is called circular dichroism, okay, which is an optical method, okay, that is a spectroscopy method, actually an optical spectroscopy method, which there is a difference in the absorption of polarized light, okay, of circularly polarized light in some molecules. So this is a method to characterize the secondary structures of all kinds of materials in this UV range, okay? So the alpha helix is very different from the beta sheets, you can see here, the red one and the black one. So if I get some solution, it works mainly in solution. So if I get some solution with all kinds of compounds and I want to follow the formation, the change in the formation of the peptides or the proteins, I can use the circular dichroism and then to characterize them. So a gun that I put in the first act will shoot in the third act. Okay, so remember this one. So the motivation and goals, I will show you phase transition phenomena now, actually, which change the morphology, the symmetry, the secondary structure of the peptides by CD, for example. I will also show you that they possess nonlinear second harmonic generation light, okay, so this kind of peptides. And then the more application-oriented by means of integrated optics by peptides, biolaser, which is our next development, biocompatible markers, and more. Okay, so now I'll show you a very interesting characteristic of this kind of peptides, which we discovered about 10 years ago, maybe even less, which we call it thermally induced phase transformation. This is a photo of all kinds of peptide microstructures that we develop in the lab. For example, if we take the diphenylalanine, which is composed of the 2-phenylalanine amino acids, which is here. So we get very long, okay, very long microtubes with hexagonal cross sections. If we add another phenylalanine, so we get the 3-phenylalanine, we get something like that. We call it microplates. Okay, so it's a different, completely different morphology, as you can see here. Very interesting, but if we add, this was done with water as a solution, but if we change the solvent, for example, to chloroform, we get all kinds of, you see, from the same amino acids monomer, we get circular spheres. Okay, so the same compound, but give us different morphologies. So it's very interesting because we can vary or control on the structures that we want to make. And there is another one, another nice D-leucine, which is another amino acid that we investigated, also very similar to the diphenylalanine. With the, as you can see here, it doesn't have any aromatic change, which is the carbon that you see here. So we characterize their morphology, and then we notice that if you heat in a high temperature, these kind of peptides, they are changing. You see here there are all kinds of hairs, the microtubes of the D-leucine is changed to all kinds of very long and very thin tubes, nanotubes. So from micro they turn to nanotubes. So we wanted to see what happens during thermal inducement. So first we measure the X-ray XRD to investigate the crystalline structure of these kinds of peptide architecture. So as you see here, before heating, we have an asymmetric non-centrosymmetry crystalline structure, which is a C6 point group. And after heating, the crystalline structure changes into orthorhombic D2H with centrosymmetric. So I will talk soon about what it means, centrosymmetric and non-centrosymmetric, but this is a first big change that we see that heating induced in these structures. For the triple F nanostructure, it's a little bit different, so also there is some kind of change. Then we also wanted to measure what is happening to the intermolecular bonds. So we use the Raman spectroscopy. I don't know if in the school they talked about Raman. No, so forget it. But it's also we can follow, let's say, the changes. You can see here in this number is gradually growing, okay, during heating. So there are many changes when you heat this kind of peptide structures. And the most interesting thing is that, this is the mysterious phenomenon that now I will talk about, is the appearance of visible fluorescence. We don't understand yet the full mechanism why it happens. I will show you later a new paper that was published by our group, which we have some maybe idea what is happening. But this kind of fluorescence, which I think that yesterday Shank maybe talked about quantum dots fluorescence and other biology fluorescence. So for now, only the GFP, the jellyfish, from the jellyfish, the green fluorescent protein is known as transmitted fluorescence light, okay? But these peptides, which are not GFP, okay, are also emit fluorescence light in the visible range, which is very good because they can be used for the future as biocompatible quantum dots, for example, which is highly recommended because quantum dots are very toxic. So there is a very close relation between the amyloid fibrils and our peptides, because about 5 years ago, this phenomena of fluorescence in the visible range was also discovered in the amyloid fibrils, as you can see here. Okay, so this is excitation and emission in around blue region. So no one knows exactly what is happening, but we discovered that what is happening in amyloid fibrils, this appearance of fluorescence is very similar in our peptides after heating. So this is our aim to explore. Sorry? Very low, 30%. So it's not, it will not be today or tomorrow or today after quantum dot, but this is our goal. So first we want to understand why we get fluorescence in the visible range. So now I shoot with in the third act. So we use the CD, okay, and we investigated there is some change, as you can see here, some change here and here, and here it's very distinctive, and some change in the secondary structure. So what is happening is that after heating, the peptide's structure, molecular structure, becomes, the secondary structure is changing, and it is now beta sheets. Beta sheets, secondary structure, are very rich and composed of hydrogen bonds. So these hydrogen bonds, remember it, because I will talk about them in a few more slides. So in everything, also in FF, triple F, and dileucine, we get this kind of hydrogen bonds, very rich hydrogen bonds, a lot of them, and beta sheet secondary structure after heating. Okay, so this is dependent on temperature of heating, of course. Okay, so you see here the hydrogen bonds in the beta sheet secondary structure. So we blame the hydrogen bonds as the source to this fluorescence. So we also measured optical absorption. I show you all kinds of optical methods to how to characterize materials. I think that some of them you already talked about in this school. So absorption also, we see here all kinds of peaks. Here there is also a small bump. And then we can see that there is absorption peak in 360 nanometers, which is our excitation wavelength. And I think that this is the most conclusive or distinctive characteristic, that you see how gradually there is a peak that arises with temperatures. Okay, so this is in 430 nanometers, which means that our peptides emit blue light when the temperature is rising. Okay, so the thing is to understand why it happens, because it happens also in the LL nanostructures, which is very peculiar because it does not contain any kind of aromatic chains, but also in the FF, which contains aromatic chains. So probably this is not the source. So we scientifically think about what is the source of this kind. As you can see here, what is the source of this blue region photoluminescence? For example, if we take DLL nanotubes, the FF microtubes, the triple F spheres, it doesn't matter if it's spheres or plates or whatever you want. After heating, they emit blue light when they are excited in UV. The same thing is for the green region. You can see here. After heating, before heating, nothing. You can excite them with UV light, you get nothing. After heating, when you excite them with UV light, you get beautiful, very strong green fluorescence. Okay, so the published publication recently published from our group suggests a mechanism which is very complex, done with DFT. You know what it is? The density functional theory. It's a mathematical computational method of quantum mechanics in all kinds of organic compounds is used and much more, which we thought about what is the source of this mysterious photoluminescence. And the consequence was that we think that there's something called proton transfer caused to a reduction in the energy bands of these kinds of materials. A reduction of energy bands results in a redshift of and appearance of photoluminescence in the visible range. So this is still under investigation, but all kinds of calculations were done showing this reduction. Here is a change of geometry as a result of this temperature inducing. So if I want to summarize, I showed you all kinds of morphologies of bioinspired peptide nanostructures, okay? Although they are from different origins, the common thing is that the appearance of visible blue and green light as a consequence of heating. The common thing to all of them is the formation of beta sheet secondary structure, which is very rich in hydrogen bonds, which probably caused to a reduction in their energy bands. And there is a deep modification of all their electronic and optical properties which followed, of course, by the appearance of this strong visible fluorescence. So this is part 1. Part 2. 10 minutes? As quick part 2. So I will do it very fast. So in part 2, what is nonlinear optics? I guess you know it already. Nonlinear optics is a light-matter interaction process, usually related to non-centrosymmetric materials. It happens only when the intensity of the light is rather strong. So all this kind of polarization cannot be emitted. And it happens only in non-centrosymmetric crystal classes. Among the 32 crystal classes, only 21 of them are non-centrosymmetric. And these non-centrosymmetric materials can show the piezoelectric effect, which is the relation between force and strain, mechanical strain, and the second harmonic generation, which means the double frequency of light or half the wavelength of light. So luckily, our material is non-centrosymmetric, otherwise it would be boring. Okay? So you can see why second harmonic generation and lack of inversion symmetry. Here is the math, but I will not, because I'm the last one, I will not discuss about it. But eventually, the chi2 is vanishing in centrosymmetric materials. Why to use nonlinear optics? We aimed it especially to microscopy, and is now used to monitor after collagen or all kinds of compounds in the human body, okay, which are non-centrosymmetric. And all kinds of pathogens and changes can be viewed, especially in nonlinear optics microscopy. You can see here all kinds of collagen gels, human ovary, cancer cells. Everything can be imaged with the SAG images and can be followed. Okay, so we can follow the changes, which is very important, estimate the size with this kind of phenomenon. So luckily, as I said, our materials, both the FFF and the FF peptides, are non-centrosymmetric, so they can be imaged in this kind of, as you can see here, setup of nonlinear optics. This is the images that we see something, okay? The refractive index of this kind of peptides can also be estimated from other microscopy technique, which is interferometric phase microscope. So we can, if we know the thickness from, for example, AFM, and we get the OPD, which is the phase delay of, for example, our peptides, we can estimate the refractive index. I do it very fast, actually. We did it to, for example, find the effective chi or the effective to understand what is the effective of our peptides. For example, in FF, we get the 24 picometer to volt, which is very higher even than collagen, close maybe or higher than lithium niobate, which means that it is very good material. And if we use, for example, a bundle of this kind of peptides, so we dense it and take a very large amount of peptides, we actually can see the second harmonic generation conversion. So the experiment of what you see here is emitting, we use an IR laser with 1064 nanometers, and this image was done in a very dark room with high exposure camera, and we see here a very small green light, which means that there was a frequency conversion. We also show here, I can show you here, non-linear, you see here, and linear waveguiding. The non-linear waveguiding is only on the clade of the tubes. This all kinds of application. Here we got a polar map, and then we tried to understand what exactly is the dipole orientation of this kind of materials. So I have a little more time because I want to show them a small. Okay. And we did something very interesting that we measure with the electro-optic effect. Okay. So here we use the special technique that is known as Pokel's linear electro-optic microscope, which is actually here is some kind of Mach-Zehnder interferometry microscope with Pokel cells. Okay, the Pokel cells will be used, I will explain to you later. So here the two arms recombine, and there is a phase and amplitude of the images. Okay, this was, we use this to understand how strong is the electro-optic effect. So if we take like a peptide tube, for example, which is very, as you can see here, very long, and we used in the microscope setup that you saw earlier, we used and we applied an electric field. We can get the amplitude and the phase. The amplitude is related to the phase difference that was here. Okay. So we want to characterize the delta n or this kind of tensors. Okay, and the phase is related to the polarization. So the Pokel cells is to translate the amplitude to the difference in the phases. So this is why we call it we need the Pokel cells. And the most interesting thing that we discovered is that each kind of peptide, for example, here we measured the FFF microplates, it contains multi-domains. This was a shock to us. We didn't expect it to be, and we don't understand why some microplates have all kinds of domains. You see here the different, here is red, here is, I don't know what color it is, I'm colorblind. And this is another red, okay? But it's not completely everything is red. So this means that there is multi-domain, so the polarization is different along the tubes or along the plate. So we don't understand why it happens, but it's interesting. So we published it, of course. And we see that domain 1, for example, domain 1 and 3, you see here the polar points are very similar. And 2 and 4, also common. So we can use them to engineer our peptides to all kinds of ferroelectric, or not ferroelectric, to all kinds of polarization and domains. So if I want to summarize this, this part, is that we used all kinds of methods to show that we get nonlinear optical response in our peptides. We also showed spontaneous domain. We measured, we found the electro-optic coefficient, and also we showed you nonlinear waveguiding and all kinds of applications, whether for waveguiding, whether it is for a bundle or for a very large amount of material that can be used as coating, for example, to nonlinear. And the last thing that I want to talk about is the peptide integrated optics. So I think there was yesterday a very nice presentation about integrated optics, so I put the word peptide in front of it. So this is, of course, the next generation circuit platforms, and the aim is to design a complete chip, all based on photonics. For example, we start with laser, filter, modulator, everything on a single chip. As you can see here, this is, of course, for routing, for optical communication, of course, sensing, everything, data centers, whatever you want. And there is much effort today to make all kinds of chips. Okay. So there are many materials that are used for this kind. Of course, silicon is the primary materials, but there are all kinds of polymers that can also do this kind of chips and the photonic integrated circuit. So now I want to show you about all kinds of organic and biological waveguides that are the building blocks for these kinds of circuits. For example, if you can see here, E. coli, everyone knows the the germ. It's not very nice. It causes to diarrhea, okay? But researchers published in 1913 a waveguide from E. coli, biowaveguides. Also spider silk, you know spider silk, that everyone see it, also are used for very strong fibers. Of course, spider silk is very strong, okay, very rigid. And they are also used as all kinds of waveguides. You see here one spot and the other one. And this is the really biological waveguide, but there are all kinds of organic. You see all kinds of structures, morphologies, whatever you want. Polymer fibers, organic hexagonal nanosheets. So the advantages, of course, they are very easy and fast to produce, biocompatible, which is very important if you want to make a biochip, I don't know, insert it inside the body, or that it will connect to parts of the body. The properties could be very easily tuned. So we can do it also with our peptides. So there are two, there is a method that I will discuss shortly. First, we need to understand what we need, how to make this kind of waveguide. So of course that we need that the refractive index of the waveguide itself is larger than the clade, whatever if it is air or a substrate, whatever you want. And we have the dimension that we need. If we talk about planar asymmetric waveguide, we get this kind of relation between the thickness and the wavelength. So here you can see an image of all kinds of peptide elongated nanostructures. You get stripes. This is very nice. You get a rectangular cross-section, which is also hollow. All kinds of small roads. Okay, so we have a very big diversity. So we can design whatever we want. But the main problem is, as you can see in all these pictures, is that are not oriented. There is a big mess. Okay, you cannot control the direction or exactly the location that you want to bring them. So there is a very big problem. You cannot use this kind, okay, of peptides. So if you want to design a special waveguide, you need to differ it. So there are two types of waveguide that we will discuss: active versus passive. So active waveguides absorb the input laser light and propagate the emitted fluorescence. So it happens only in material that show all kind of photoluminescence and fluorescence. For example, as you can see here, since it is luminescence, any point that I will radiate as an input light, I will show at the end, as you can see here, I will always see the output light. Okay, this happens in active waveguide. But in passive waveguides, okay, passive waveguides are like normal waveguides. They directly propagate the laser light. They're not connected to fluorescent. This is why they need special light coupling in the input light. So not in every place you can radiate like here and also get at the end. You need only when there is a specific coupling of the light in the entrance, only then I will see at the end the light. Okay, so here you see all kinds of polymers, organic tube, something like that. So as I told you, first we numerically simulated our peptides, and we showed that we can get passive waveguiding. Okay, so here we use in horizontal way, in vertical way. Okay, and now I'll show you a small movie. So this is experimentally results. So first we see that we get, you see in the end, if we couple, since there is a good coupling of the input light, we always get an output light. So if we use all kinds of lasers and LEDs, so for example, we used white LED, we get at the end white light. If we used red LED as excitation, we at the end we see here the red dot. Yellow and green are very strong, okay? Not by accident. We understand it from the dimensions that I talked about. The best coupling is in this kind of wavelengths, and also we get blue. So actually we can get all wavelengths that we want. Now I will show you, here is a white light, a small movie that shows how we get the passive waveguiding. So it's a very short video, but it's very nice. So only when there is coupling, you will see a light at the end. Okay? So look carefully here in this small movie. Okay? Whoa. Whoa. Okay? So I'm excited every time that I see it because I can't believe that we managed to do it. It is very difficult to do. You see, if the laser spot is here, you get nothing. But when there is a perfect coupling, okay, then we see the end. This is passive waveguiding. If it was only fluorescence, any place that we were, that's it. Okay. Any place that we would excite it, we got at the end. Okay, so we did it for the microplates, tapes, the FF tubes, which are hexagonal, so the shape does not really matter. But you see only when the spot was here, we get something in the end. When it was here, nothing. Exactly for the other FF tube. So I talked about at the beginning, or 3 slides ago, I'm about to finish. So 3 slides ago, I talked about the problem of the peptides, of the disorientation and the lack of the ability to control them. It's a very big problem because we cannot use them as photonic compounds to do something with them. Otherwise, they're just a bundle or messy materials, into very disoriented, and so we needed to thought about a method to control them. So we use 2 methods. First is the top-down method. We use the focused ion beam, if you know what it is. I don't know, but this is more a nanotechnological approach that is used as ion beams, okay, to mile or drill the material that we want. So this is a brute force top-down approach. We take some kind of peptide belt, and then we can actually do whatever, can fabricate whatever photonic or integrated photonic circuit or device that we want. For example, we did splitter, Mach-Zehnder. You see here splitter with 2 gratings. So this works very good. I will show you the next slide. And there is another possibility to use nano fountain pen. Nano fountain pen is a method in which a cantilever of an AFM, let's suppose that everyone knows what it is, a cantilever of an AFM with a hollow tip, that inside the hollow tip we can insert a solution, and then it dries and can be directed at whatever direction that we want, at every position, anywhere we can use it to fabricate like all kinds of spheres, dots, lines. So, but this is very tough. This is much tougher approach than this one. So if we take very large, that we found very large peptide structure, this is a large plate. Okay, this is like a mini wafer with size of like 40 microns, which is very big, that we can do whatever we want about it. We use the fib, you can see here. For example, we created splitter, Mach-Zehnder, okay, with gratings. We can also put it in between electrodes, okay? So very nice. Then we show the passive waveguiding, which you saw the movie earlier. So we can do the one-dimensional passive waveguiding, which means that the light is in one direction. If it is very big, we can do a 2-dimensional waveguiding. You see the light is here, this is simulation. Light is here, but you get in all kinds of positions the output light. And we managed to show that we indeed made a complete peptide splitter, which is a very fundamental photonic device, to increase the light coupling, we use grating at the input, 2 gratings at the output. So if we emit, we excite our peptide splitter with white LED, we get 2 blue LEDs, okay? The 2 blue lights at the end, which is, of course, a proof that our device works properly. And we also show that we can get active waveguiding, because if you remember, our peptides can show fluorescence, okay? So this is why they can be used also as passive and active waveguides. As you can see here, this is experiment, simulation, and that's it. So for some of you, see 3 minutes. So we begin. Yeah, so what I showed you is that when you take the peptide monomer, after self-assembly, we get, for example, plates, tubes, hexagonal tubes, whatever you want. If you want spheres, it could be spheres. And then we can, in our materials, we can make them passive optical waveguides or active optical waveguides. In passive optical waveguides, we don't care about the secondary structure. We don't care at all. All we need is a good coupling of the input light to get the output light. But if we want to use them as active optical waveguides, we need to heat them, to make them fluorescent, and then we don't care in the coupling, but we need them to be fluorescent. The way to do it, if we want to make special devices completely made of biologically waveguides, then we need to use either nano fountain pen or focused ion beam or other method that we still didn't invent or thought about. But these are the 2 things that we used already. And that's it. We can further the research to make more devices, to make them interconnects between chips or whatever. So thank you very much.
I think that we finished nice. Any questions? Yes, please.
You said that in order to emit light, you heat it up to 180 degrees. If we go back to room temperature,
No, nothing. It's irreversible.
It's irreversible. You ruin the specimen. Okay, thank you.
And what is the reason of this? How do you explain that if you heat it up to 100?
Because there is a molecular rearrangement and they cannot go back. That's it. They finished their story. Okay, this is the feature of the material.
So it's one use.
Yeah, one use. Or you can use it as a coding or something else that I didn't show you, but we can do it, for example, as a ID, special ID, which is fluorescent. You can heat it once, or you can detect if there was a heating because the properties are changing.
Hey, can I ask you on this? Is there any thermal damage of this kind of devices? So, excuse me?
What's the lifespan of these applications?
Yeah, but if you increase the temperature, is there any...
Yeah, if you put above 180, they're melting.
Okay.
Yes. How do you measure the changes in Chi2?
The changing in Chi2,
After you put it in 180?
yeah, it disappears. Nothing, yeah. Because it from non-centrosymmetric, it transformed into centrosymmetric, and then you can... Yeah, the temperature does this kind, and then you cannot see nonlinear light, but you gain photoluminescence, so...
Do you think that you can change this symmetry by using laser light instead of temperature?
Yeah, I know that we did it. We managed to do it. The laser light itself is locally heat, and then we get all this... so it's very nice.
Very fast technical question, just to think about. When you measure the second harmonic generation, what is actually the geometry of these tubes on a surface? What is the geometry of the sample?
So we put it, for example, on glass or on quartz, okay? Yeah, and we use the bundle, or we concentrate on a specific tube or a hexagonal tube, or one tube.
Yeah. And what is the maximum dimension of plate, tight plate?
It is very varied. It could be from a long of 20, 10 microns to 100 and even more. Thickness,
The diameter.
diameter or thickness, if it is a plate, the diameter is around 300 nanometers.
Diameter of the plate, I don't understand.
No, the thickness of the plate is about 300 nanometers. If you talk about diameter of, for example, the hexagonal, it could be 1 micron, but even less. Usually it is in the nanometer size.
We can't discuss.
If you want to ask me about Roland, I can also answer. About the Eurovision, everything.
Any other question? So if not, let's thanks again Amir.
Thank you.